Continuing on 11.3, and we're looking at op-amp applications, and the next one we're going to look at is called the integrator. And an integrator is a circuit, among other things. You can use an integrator if you have a, for example, if you had a positive or a square wave coming in, you can get a shape that's almost rectangular coming out of it, and that's the kind of circuit that we're going to be looking at here. They can be built around an RC time constant with R1 and C1. So here is the value of R1, and here is C1 up here. So 33K and 10 nanofarads are the components that this is actually built around. But let's take a look at this circuit. Let's see, we've got R3 here. This is going to be RB, so we can basically ignore that. So we have a signal source coming in, and in this case it's going to be a rectangular or a square wave. And it's going to be fed through R1, and this is going into an inverting amplifier, so the output, as the input goes positive, the output will actually go negative. And note this, it goes in here, and then here is the output, and the output is fed to a feedback loop through R2 and C1. So the idea here is that we're going to have a signal come in. It's going to see the virtual ground right here. So there will be that voltage across this resistance. There will be a current, and since it's a square wave, it will be a constant current for as long as it is positive and as long as it goes negative. That current is going to be fed up to the output, and it will charge this capacitor. And so that line that you see, that rectangular shape you see, is actually the charging of the capacitor in the feedback loop. Okay, a few things that we need to consider here. Let's see, we looked at R1 and C, okay. The input voltage is felt across R1 to ground. Okay, we talked about that. The current is fed through the feedback loop and charges the cap based on the time of the input. Okay, this is an important thing, based on the time of the input. So we have to calculate what is the time. Now, if this were a 1,000 hertz signal, then the time of 1 would be, 1 over 1,000, and that would be 1 millisecond. And since we're looking at a square wave, and this would be the whole cycle, and we're going to be looking at the charging time of the positive cycle and then the charging time of the negative cycle, but we need to separate them out. So we're going to take this and divide it by 2, so we would have 0.5 milliseconds would be our time. And so when we put this into a formula, we need to be able to specify the right time that we're going to be using. Now the next page here is this same circuit, only it's larger so you can actually see it. And we have the signal source here, and we have the oscope readout. And this was a simulation from Workbench where I've captured the output and the actual circuit. Now this is the formula we'll be using, and this is going to be VI times T. So that'll be the input voltage times the time, and then that will be divided by this RC time constant, and that will tell us the output voltage. So what we're looking at is we're going to be sending in a specific voltage for a certain amount of time, and we're going to see what will that develop through in the charging of this capacitor. What kind of voltage will we see? And you see the results over here, that the square wave is the input, and this rectangular shape that you see here is the output. But let's do the formula, and so let's pull up our calculator and let's see what we're going to get here. Okay, so first of all, we need to look at the time, and so we said we had 1,000 1 kHz as our input. So let's just do 1 over, and that gives us the 1 millisecond. That is the time of one cycle. And then we'll divide that by 2. So that is the time, that is our time right here. And then if we look at our square wave here, and we can go down here and observe that this is a 1 volt peak signal. So we would take that times 1. I guess we don't need to do, times it's going to be the same value. So that is our numerator. And then we would divide that by and this is going to be the RC time constant, so it would be R1, which is 33 exponent 3 times, and this is 10 nanofarads, so that would be 10 exponent minus 9, and in parentheses, and then equals. And you'll notice that value is 1.51 volts. Let's write that down, 1.51 volts. So what that's saying is that during this positive cycle, that there's going to be a current through this device that's going to charge this capacitor, and it's going to develop a voltage. Now, during this time, you'll notice the voltage appears to be, it's going negative. Well, the reason it's going negative is because this is it's fed into the inverting side, so as this is positive, the output's going negative, which you would expect. And as the peak voltage goes negative, you see the charging of that cap going positive. Now, the question here is, what is the value of this triangular signal? If you go down here, you can see right here that the value is 1.447 volts. That's from the bottom of the triangle to the top of the triangle. And remember, our calculated value was actually quite close to that value. And when you're doing this, the input must be a peak-to-peak value, and V1 would be the peak value. So this is a quick look at a circuit called an integrator.